This is example 2 from lesson 2.11, definition of continuity. So we have a piecewise function that's shown on the graph as well, where x is less than or equal to 0 and where x is greater than 0. So we want to look at the function at the value 0 to see if it's continuous or discontinuous. Now I know that when I look at x to be 0, I have a point that's defined, and I also can see the limit from the left and right are equal. So at x equals 0, this is going to be continuous. There's no holes or gaps at 0. However, when I look at this value -4, I do see a point of discontinuity. So this is going to be discontinuous, and we'll prove that in a second. We'll also prove that there's a discontinuity at x equals 4 because we have a vertical asymptote. So we're going to prove that algebraically as well. And this is 0. So where do those values all come from? It comes from the non-permissible values of the function. So when I have less than 0, I know I have to have values that are to the left or equal to 0. When it's greater than 0, I know I have to have values to the right. But again, where does 4 and -4 come from? If I simplify the function in the numerator and denominator, I am going to see non-permissible values. And the non-permissible values are at -4 and 3. You do not have to worry about the 3 because it's not in that domain. But I do have to worry about -4. The second piecewise, I have a non-permissible value at 4. So the three values that I need to check are 4, which I know is my asymptote. I need to check -4, which I know from the graph is my point of discontinuity. And I also have to check 0 because that's where the function is changing. So once we know what we're looking at, we're going to prove everything algebraically. So I'm going to check x equals 0 first. And the first thing I'm going to do is evaluate the function at 0. Now if it equals 0, then I know that I'm going to choose this function because of the equal sign. So I have 3 brackets 0 plus 12 over 0 squared plus 0 minus 12, which evaluates to be -1. And again, if you look at the point, I can see the y value is -1. The second thing I'm going to do is evaluate the limit. Now the limit I'm going to evaluate from the left and the right because that's how the function and the piecewise is defined. So to the right of 0, I'm going to choose this function because it's greater than. So I'm going to substitute my value in 0, and I'm going to get -1. For the left, I'm going to substitute the value into the first function. So I'm going to get 3, 0 plus 12, which is very similar to the very first thing I did above. And I'm going to get -1. The limit from the left and right are the same, so I can make the conclusion that the limit as x approaches 0 of my function equals -1, and the limit does exist. The third statement and the final statement is f of 0 must equal the limit as x approaches 0 to be continuous. And in my case, if I look at the two values, I can see that is true. So f of x is continuous. There's no holes, there's no asymptotes, it is continuous. So now I'm going to do a second test point. I'm going to check x equals 4. So the first thing I do is evaluate the function at 4. So which function do you choose? 4 is in this domain, so I'm going to use my function x plus 4 over x minus 4. So 4 plus 4 over 4 minus 4 gives me 8 over 0. Now this is undefined, which verifies that I do have an asymptote. Even though it's undefined, I'm still going to calculate the limit and determine what kind of discontinuity I have. So Because I know I have an asymptote, I have to check the limit as x approaches 4 to the right and to the left. So 4 to the right of x plus 4 over x minus 4, and the same thing to the left. I know the answers are infinity because I know I have a vertical asymptote. The question is it positive or negative? So you use your test point, like 4.1, and when you plug it in, you get a positive. If you plug in 3.9 for the left, you will get a negative. So this statement here is proving that the limit as x approaches 4 of my function does not exist. And we always should write the third statement just to have everything completed. So f of 4 does not equal the limit as x approaches 4. So we make a final statement and we're going to say f of x is discontinuous, which makes sense. I have an asymptote there at x equals 4, and we call that a non-removable discontinuity because the limit does not exist. And the third and final check will be the other non-permissible value was -4. Now remember what happened at -4 on our graph? It was a pod. So f of -4, again, which function do we choose? Just to show you, -4 is in this interval. So I'm definitely going to use this function. And I'm going to substitute it into the original to prove something to you. So f of -4 would equal 3 bracket -4 plus 12. I'm going to plug -4 in here, -4, subtract 12, and you're going to get 0 over 0. Now 0 over 0 is undefined. We need to first prove that the function is undefined. However, when we calculate the limit as x approaches -4, we know that the function simplifies. We already did that above, so I'm just going to show you one more time. And you see that the factor cancels, which verifies that we do have a point of discontinuity. So now we have this function remaining, and when you do substitution, you're going to have -3 over 7, which means the limit does exist. However, even though the limit exists, the function was undefined. So f of 4 does not equal the limit as x approaches -4. So what do we say about the function? It's discontinuous, and we knew that because we had a point of discontinuity. However, what kind of discontinuity it is called removable, because the limit did exist. So it's a removable discontinuity. That's it.